So a charged particles, we're not told if it's an electron or not. We're just told it's a charged particle traveling horizontally with a speed when they enter a vertical magnetic field. Okay, so we're dealing with magnetic field. If the radius of the arc of the deflected particles is such, what is the charge to mass ratio? So what we're told here is that it's traveling in a circle because it says there's a radius of an arc. Well, to have a radius, I need a circle. Okay, so we know it's circular motion and that it's a magnetic field. So I can make that assumption that Fc is equal to Fm. And I'm going to do what we just did, but I'm going to do it again just because it's practice. So try, I won't go through every detail, but you can just do it with me. It's good practice rather than just copying because you'll have to do it on your own. So what I'm looking for is to get a value that gives me that Q over M, okay? So I'm going to take my speed, my radius, and my V perpendicular and plug that into that formula that I just made, okay? So my V, 3.6 times 10 to the 6. So my Q to M ratio then to sig digs would be 5.34 times 10 to the power of 7. And my units will be, charge is always in coulombs, right? And my mass is in kilograms. So make sure you put your units down. Okay, so now the next one we have a different scenario going on. It's asked what's the speed of the electron that passes through an electric field. So just electric, we're not talking about magnetic. Oh, sorry, and a magnetic field. So there's both electric and magnetic. Assume the magnetic field and electric field are perpendicular to each other. The key word here is undeflected. So think about it, it's not going up or going down, okay? So this is a very important word. When you see those words undeflected, that means if we drew a free body diagram of our electron, and we're not told which way the plate is going or anything, but say this is Fe, okay? That's one force that's acting on it, and the other force that's acting on it is Fm. If it's just moving straight and not being pulled up or down, then we can know, because we know our F net is equal to Fe plus negative Fm. So F net then is 0. If it's not being pulled one way or the other way, those forces need to be the exact same. So now I can assume that Fe is equal to Fm. So again, see how we're incorporating our knowledge from Unit B? And it's important to be able to interpret the question, see which words are important, and apply them to making your own formula. So again, let's expand our forces to have equations that are valid for these questions. So we're told an electric field, okay, so that's our E with an arrow, 6.3 times 10 to the 3 Newton coulombs. And we're told our magnetic field is B perpendicular, 7.11 times 10 to the negative 3 Tesla, okay? So I want to expand Fe and Fm so that they include those variables, as well the speed. That's what I'm trying to find out. I'm trying to find out speed. So I need formulas that will include these variables. So let's check out what we have for FE. So we have FE is like the K Q1 Q2 over R squared. That one's not going to work because that one can only be used for not in parallel plates, right? That's like two planets apart from each other kind of thing. So which one can we use? FE is equal to E times Q, okay? So we're going to make this one E times Q. And our FM, we need to have B perpendicular and speed in there. So I'm going to use my Q times B perpendicular. Okay. So this one is more simplistic for rearranging, which is nice. So I have Q on both sides, the top of the fraction, so I can cross those out. And I want to rearrange to solve for V. So then I know my V is equal to E divided by B perpendicular. 6.3 times 10 to the 3 Newton coulombs divided by 7.11 times 10 to the negative 3 Tesla. So my speed then is 8.86 times 10 to the 5 meters per second.